All right, guys, we're going to solve some gas stoichiometry problems. So let's start on page 461. We're going to take a look at question number 38. So this reads in the textbook, how many liters of propane gas will undergo complete combustion with 34.0 liters of oxygen gas? So I've just sort of sketched out, so how many liters of propane complete combustion if I'm using 34 liters of oxygen. So obviously this is gas stoichiometry, so we have to have a balanced equation. So let's get that done. So C3H8 reacting with O2, and this is a gas, oxygen is a gas, and complete combustion, we know at this point in our chemistry careers that complete combustion always gives us carbon dioxide and water vapor as the products. So this is a known entity to us, a known idea. So now let's look at what we have to balance. So we have 3 carbons on this side, so that means we'll need 3 carbons over here. And we're going to leave the oxygen to the end since oxygen is in both places here. So we have 8 hydrogens over here, so we need 8 hydrogens over here. We can accomplish that by 4 times 2. And now let's count up our oxygens. 3 times 2 is 6, plus 4 more is 10. So there's the 5. And you remember this was actually an equation that was balanced in the lecture as well, all right, as we're looking at the combustion of propane. So now, if we have 34 liters of oxygen, so the balanced equation says that the ratio is 1 to 5 or 5 to 1, but we don't want to start there. We do want to start with the data that our problem gave us, so 34.0 liters of O2, and we now have this basic understanding that our coefficients not only give us mole ratios, but they give us volume ratios. So I want oxygen to go down here because it has to cancel. So 5 volumes of O2 gives me 1 volume of C3H8, right? And then that's all I need to do because so oxygen cancels. I'm going to be left with a liter volume for C3H8. Sorry about that. Get tongue-tied. And I need a calculator. Oh, there you are, calculator. All right, so let's run these numbers here. So 34 divided by 5 gives us 6.8 as our answer, and it's 6.8 on the dot. But I'll need to add a 0 because I had 3 sig figs here. So 6.8 liters of C3H8. So there is the final answer. So just a little one-step problem, right? Where we are using our volume ratios, much like we used our balanced equation ratios instead of for moles. Now we're understanding that this is also volume. All right, now let's look at the next question on this page that we're going to solve together. So this is number 39. Number 39 says determine the volume of hydrogen gas that reacts completely with 5 liters of oxygen to form H2O. So again, we need a balanced equation. So hydrogen gas reacting with oxygen gives us H2O. Gas and gaseous. And now we're going to balance this. So the hydrogens are okay, right? 2 and 2. But we have 2 oxygen on this side, so we have to have 2 oxygen here. So the only thing we can do is put a 2 there. Now we recount the hydrogen. 2 times 2 is 4. So I need 2 over here. So now we can quite easily, maybe even easily, ascertain that this is a 2 to 1 relationship. But just in case this was not a nice even number, how do we show our work? 5 liters of O2 using the volume ratios from the balanced equation. So 1 volume of O2 for every 2 volumes of hydrogen needed. So O2 cancels. 5 times 2 is 10.0 liters of H2 gas. All right, so that's how we solve that. The volume unit we get to pick up from here because we're in liters. That doesn't change for us. All right, let's do another one here. Let's go on and do question number. This is one that is not in your work. So let's just read this just quickly to again work this out. Sorry, let's. All right, so here we have this is. Ethanol. Okay, so ethanol is burning in oxygen. So we see it's already balanced 1, 3, 2, 3. All right. So how much carbon dioxide, what volume of carbon dioxide would I get if I'm burning in the presence of 6 liters of oxygen? So 6 liters of O2. And again, 2 volumes of CO2. 3 volumes of O2, all right? So 3 divided by 6, 6 divided by 3 times 2, so it gets us 4 liters of CO2 will be produced, all right? Now, here's something to just think about. If this was at STP, if this was happening at STP, could we determine the mass of this? Yes, we could. So we would take this 4 liters. So 4 liters of CO2, if it told us it was at STP. And then we know that 1 mole has a volume of 22.4, right? And then we also know that 1 mole of CO2 has a mass of 44 grams, right? So I could figure out the mass of that at STP if this truly is happening at standard temperature and pressure. So that would be 4 divided by 22.4 and times 44. So that would be, and we can only have 1 sig fig, so we'd have to say 8. We'd have to say 8 grams there. It's not good sig figs, is it? 8 grams of CO2. If it wasn't at STP, then I could use the ideal gas law, PV equals nRT. So this is the volume at STP. But I'm pulling forward information from the last chapter, from the last section. So if I don't have STP, if I have a different pressure and a different temperature, then I would just plug those in. There's my volume, right? I would solve for moles and then use the molar mass. So a lot of ways for us to think about how these problems come together. All right, let's keep working now. Let's do this problem. This is on page 40. This is on page 463. This is number 42. All right, and let's see what we can do here. So number 42 tells us that we have ammonium nitrate, and it's decomposing into nitrogen dioxide and water vapor. So this is not a gas. This is a solid. These two are gases. That's okay. We can't determine anything about the volume of this solid, but it actually is not asking us that. It's asking us for how many grams of that. How many grams of this will we get if we use 1 liter of this? And now we're at STP. So let's think about how we can solve this problem. Well, we're going to start with just the same kind of idea that we used in the last problem, which is because it's at STP, we know that 1 mole equals 22.4 liters. So we're going to be able to use that piece of information. So 0.1 0.100 liters of NO2, all right? And this would take up, so this 1 mole, 22.4 liters, because we're at STP, all right? So let's get that answer right there. So that would be 0.1 divided by 22.4. So this gets us 0.00. Make sure I don't make a mistake there. And we can have 3 sig figs. So we're going to say 446. 446 moles of NO2. Well, now that I know how many moles that is, I'm just going to use basic stoichiometry, right? I'm going to continue like this was a standard. So the gas part was using this. Now I'm just standard stoichiometry. 0.00446 moles of NO2, right? What's the balanced equation ratio? 1 mole to 1 mole, right? 1 mole of NH4NO3 to NO2, right? So mole cancels. And that's 1 to 1, right? So that's going to be 0.00446 moles of ammonium nitrate, NO4, NO3. Now I'm going to take that amount of moles and I'm going to convert that to mass. 1 mole. So we calculate the molar mass here. So 3 times 16 for the oxygens. I've got 2 nitrogens, so 2 times 14. And then 4 times 1.01. And I have already looked that up. So that is 80.03 grams per mole. So now 0.00446 times 80.03, 0.00446 times 80.03, and we can have 3 sig figs. So there was my molar mass calculation. So 0.35, and that was a 6.9, so it's going to round to 7 grams of ammonium nitrate. So here we see, all right, so here we see that what started out as gas, as a gas problem, right, and we were able to use this idea, this was critical, right, understanding that I can do a volume calculation there. And then then this became plain old stoichiometry, right? Okay, let's see if we can get one more. Oh, that was the end. That's all we need. No, one more here. There we go. All right, so here, this is number 45. So let's take a look at this one. Here we have, this is sodium bicarbonate, and this is acetic acid, so baking soda and vinegar. So here are the products. So it says, again, this is aqueous. Okay, this is AQ. Can't read that. So 28 grams of this reacts with vinegar, and then how much of the gas can we produce? And let's see, do we have any other information? Oh, and when we read it, it says that we started at 25 degrees Celsius, but the gas cooled. So it cooled to 20 degrees Celsius, and the pressure is 1 atm. All right, and then we're asked for volume. So we've got a temperature, so not STP. Okay, so this is not at STP. So let's think about how we're going to use this information. Okay, all right, so we have a mass, right? So the only thing we can do here is do stoichiometry from the beginning. So we're going to take 28 grams of NaHCO3, and we need to convert that to moles because we know we can't compare these at all unless we're comparing with moles. So 1 mole of NaHCO3. 1 mole has a mass of 83.9. I did have that available to me, so grams is going to cancel. All right. Then the next thing I'm going to do is use my mole ratio. So 1 mole of CO2 over 1 mole of NaHCO3. All right, so that's going to cancel. So now I'm going to take 28 divided by 83.9, and that's going to give us 0.33 moles of NaHCO3. All right. Now, since this is not at STP, I'm going to have to use PV inert, right? And I'm going to solve for volume, all right? So pressure is 1. I don't know the volume. Moles is 0.33. R is 0.0821. And the temperature, this temperature, what it cooled to, is 293. Final volume, 7.9 liters CO2. I'll post the homework.